Hello everyone. So welcome back to Python Challenge for All. Let's continue our work on Fibonacci numbers. So first we defined Fibonacci numbers and then calculated using recursive function. Now the code is like this, where very simple implementation, right? Very simple, that fib n equals to fib fib n minus 1 plus fib n minus 2. Okay. Otherwise, for when n is larger than 1, for n equals 0 and 1, it's n. Okay, so using this, computation is very simple, correct? But up to, say, 20, 30, 40, it becomes very slow. And what we found was, like, for growth of 10 more numbers, we need to have kind of 100 times or 120 times slower. So it becomes like this. Maybe we should write 120, and we can write using .2f here, .2f here, to make it simpler. Okay, so from 50, it's like this: 60, 70, 80, 100. It takes almost 2 million years to calculate up to 100. And the graph is in logarithmic scale. It's linear, meaning that it was really exponential to calculate it. So let us continue. So the problem was, how can we compute the Fibonacci numbers faster? And actually there is, yes. What we see today is a Fibonacci with memoization. What is memoization? A new word, maybe. Let's see, take a look at Wikipedia. Memoization, maybe you can read it later, but is an optimization technique where to speed up computer programs by storing the results of extensive calls to pure functions and returning the cached results. Okay, let's do it here. Today, we will implement and compare the results, reducing the redundancy, recursion with memoization. The problem is with fib1 is that it computes the same thing many times, right? To calculate fib10, we need to calculate fib9, and to calculate fib9, we need to calculate fib8, and it will be done many, many times. So we can reduce redundancy by recording the intermediate results. Here, we will implement on this idea fib2 of n. Okay, let's do that. The idea is keep the known results in global list L, starting with 0, 1. So very simple. Let's try this. So now we go fib1, fib2, n. Okay. So let's define fib2. We should write memoization. Fibonacci with recurse with memoization. Okay, so fib2 of n as defined. Let's see, before that, we need to use global list. Of course, we can do it otherwise, but let's do it simply by using list starts with 0, 1, which is like here. Okay, starts with 0, 1. And then we compute successive n's using this list. So if length of L is shorter than n, only that time we do new calculation. L append fib2 n minus 1 plus fib2 n minus 2. Yeah, that's it. Otherwise, fib2 just returns otherwise or not. After that, it returns the nth element of list L. Strange, right? Okay, L is not defined. It should be equal, not minus. Okay, so here we use global list L, and let's see how it looks like. So keep and known results. Keep the known results in global list L starting with 0, 1. The new fib2 is to be kept as n sub n, where it is computed as fib, just using the same one. But only when it is new, it's computed. Okay, let's run and compare the results. To do that, maybe we can compare the two results, fib1 and fib2. Just in case, let's run fib1 definition again to compute it. And we can compute by, so of course, we need to do the list initialization each time. So for I in range, say 110 or 15, maybe, we write both. Yeah, we need to initialize it every time we try the calculation. And then print I, fib1I, and fib2I. Okay, let's compare that results. Okay, they're all the same. They're same all the time. 2, 3, 4, 5, 6, 7, 8, 9, 11. Okay, so it seems fine. Good, very good. So let's compare the computation time. Like we can copy from the previous case, the computation time here. Okay, we can copy the list, the whole code here, copy paste it down here, and then change YL1 to YL2. So and also we use, instead of fib1, we use 2, and we need to do the initialization, as I said, each time when we calculate fib something. Okay, and fib2, and of course we add the list to 2 instead of 1. So let's see it from 20 to, say, 30 area. Okay, it's quite fast. And the result is 42, something like this, 26 something. Very good, the same. The time is quite different. That last time it took about 60 seconds, but now it's 0.0. Great. Yeah, actually, can we go up to 100? Yeah, actually, we can do that. Say, so maybe we can change this to, instead of 2, we can multiply by 10 this time. Okay, so it's quite easy to go 20, 30, 70, 80, 90, 0.0 seconds. Great. Maybe we can write it this way to make it clear that it's time, 0.0. So it's quite easy to go up to 100. In the last case, fib1, it took more than 1 million years, but here it takes 0.0 seconds. Okay, very fast. So let's quickly see the computation time approximation. So here, there's only one addition. So each time there's only constant computation. This for data access. So it's like the computation time is n times constant c, meaning that it's linear. Landau notation is linear. O notation is linear, meaning that it's very fast. Let's see the code. Let's compare the code for computation. So again, we copy it and paste it here, using it 2 and commenting out y scale. And let's see how it looks like. Yeah, great. It's it's very small, so it goes up and down, but very linear. Okay? Or we can compare 1 and 2 as this, because we have 1 as well. So we can write 1 here. And let's see, we need to change this to kind of YL1. This is quite a trick, but we can compare. The first one is Fib1, and the orange is Fib2, where it's really, really constant and slow. If we use logarithmic, okay, it's going this way and it's staying here all the way constant. Okay, so the point is there is a very fast algorithm to calculate Fibonacci numbers. And it's linear, fast enough. Actually, there is a fast algorithm which computes Fibonacci number in log n time using matrix multiplication. But if you are interested, please take a look. Find it on the internet. Okay, that's all for today. Come back again next time with a little more about Fibonacci numbers. Bye.